Okie dokie. So, doing the next section that we're covering, section, where are we? 7.5. So, the first chunk the other day was this review of 7.2 and 7.3, and then covering 7.4. Tonight, I just did excuse me, 7.5 because I had a massive homework due for this class, so I only studied a little tonight. So let's get into it. Okay. How to write a given permutation in cycle notation. So, for example, if we had 1, 2, 5, 4 in the snap group S6, then we would say that 1 goes to 2, 2 goes to 5, 5 goes to 4, and 4 goes to 1. And also, since they aren't mentioned in the what looks like a 4 cycle, 1, 2, 5, 4, because they aren't mentioned, 3 and 6 just go to themselves. So 3 goes to 6. I mean, sorry. 3 goes to 3 and 6 goes to 6. So really, we have a snap group that looks like 1 goes to 2, 2 goes to 5, 3 goes to 3, 4 goes to 1, 5 goes to 4, and 6 goes to 6. So permutations, as you can see, can be expressed in cycle notation by listing elements in a cycle. Oh, whoops. Elements not listed will remain fixed, like 3 and 6 in that last example. If you had a permutation of A1, A2, all the way to AK, that's a cycle of length K, or a K cycle, since there are K many elements in that cycle. Products and cycle notation, you go from right to left, starting with the first element of right or of the right side. So if you had 1, 2, 5, 4, 3, 2, 1, then you would go 3 to 2, 2 to 5. So then you would write 3 to 5, etc. Disjoint cycles, 2 cycles are disjoint if they have no elements in common. So disjoint cycle, that's just a comparison between cycles. That's not a type of one cycle itself. So 2 cycles are disjoint if they have no elements in common. Example, 1, 4 and 2, 5, 3 are disjoint cycles in S5, but 1, 2, 4 and 2, 5, 3 are not disjoint in S5 since 2 appears in both of those cycles. Theorem 723, disjoint cycles commute in in Sn. So if we had 2 cycles, phi, that's A1 to AK, and rho, that's B1 to BJ. If phi and rho are disjoint in Sn, then phi rho equals rho phi in Sn. And you can prove that by starting out by showing that rho phi times I for identity equals identity times phi rho. Since identity is just going to make all that the itself. True or false, every permutation is a cycle. Dun dun dun. The answer is false. Not every permutation is a cycle. Example 1, 2, 3, 4, and S5 is a product of disjoint cycles. That's just what we had in our notes. I wish I had a better explanation for this. Theorem 724, every permutation in Sn is the product of disjoint cycles, each of length greater than or equal to 2. How to find the cycle decomposition for a given cycle? That's theorem 724 via cycle notation. So if you had 1, 2, 3, 4, 5. So, well, if you had going back to this. So you have this one at the bottom, 1, 2, 3, 4, 1 to 2, 2 to 5, 3 to 3, 4 to 1, 5 to 4, 6 to 6. you would write that as literally the 1, 2, 5, 4 at the top. That'd be like a disjoint cycle, or uh like if 5 ended up actually going to 2, then you have, or sorry, if 5 went to 1, then you would have 1, 2, 5, 4. Because 1 would go to 2, 2 would go to 5, 5 would go to 1, and that would be the end of that. It all loops. So once you get a loop, ugh, what the heck? But yeah, once you get a loop going, then you can write a permutation as or even without a loop. But anyway, you can write every permutation in Sn as the product of disjoint cycles, each of length 2 or more. How to find the cycle decomposition for a given cycle? Again, that's just theorem 724 and that cycle notation knowledge we covered. It's kind of a caveat to that theorem, or a precursor to theorem 725. The order of a K cycle in Sn is K. And we know that like from the definition, that was kind of mentioned for the definition of a K cycle, or alluded to at least. So now for theorem 725, we see that the order of a permutation rho in Sn is the least common multiple of the lengths of the disjoint cycles whose product is rho. And you can use theorem 723 to help prove. So again, with this kind of like precursor to 725, you see that the order of a K cycle in Sn is K, but definitely a concrete way to show that, or is the least common multiple of the lengths of the disjoint cycles. So if you were only given disjoint cycles, this would be super helpful to use, so you don't have to go ahead and combine them just to see the order. But if you had them already combined into the full K cycle, then this is pretty helpful. And you can use theorem 723 to help prove that, which was disjoint cycles commute in Sn. How to find the order of a permutation quickly, that's that theorem 725 in cycle notation, or just knowing that the order of a K cycle in Sn is K. So either way, transpositions, this is a 2 cycle, so that's like literally like one, like those permutations that are just like 1, 2, 3, 4, like shit like that. Oh, stuff like that. So here K equals 2. So for that kind of caveat, K equals 2, and for the K cycle definition, that's like kind of has implications there. Transpositions properties inverse. Every transposition is its own inverse in Sn. The explanation mark is confusing. I just meant to say Sn, and I'm very excited about it. Not Sn factorial. So if AB is a transposition in Sn, then AB equals 1, 1 in the parentheses, sorry, where AB inverse is AB. Theorem 726, every permutation in Sn is a product of transpositions, which are not necessarily disjoint or unique. But the important thing is here, every permutation in Sn is a product of transpositions. So not only can you write, what is it? Oh my gosh. not only can you write a permutation as the product of disjoint cycles with lengths 2 or greater, you can write permutations in Sn as a product of transpositions. So like 2 cycles. So again, oh, not again. This is new. So an even permutation in Sn is one that's written as an even number of transpositions. Also, a quick way to see that without having to write out all the transpositions. You know that a permutation is even if the number of elements in the permutation is odd. So like literally for ABC, since there are 3, you can count 3 elements in there, A, B, and C. Like it just works out every time that that odd number of elements is gonna give you an even number of transpositions. So kind of conversely, an odd permutation in Sn is written as a product of an odd number of transpositions, and you could kind of do a similar alternative definition as well, or just a quick way to show it or know it. So a permutation is odd if the number of elements in the permutation is even. I meant to put A, B, C, D in parentheses, but yeah, so you can count A, B, C, D, that's 4 things, that's even. So you know that that permutation A, B, C, D is odd because it just works out that way every time. Lemma 727. The identity permutation in Sn is even, but not odd. So that's nice to know. 1 is always even in Sn. Theorem 728. No permutation in Sn is both even and odd. So this is like XOR. It's a permutation is either even or it's odd. It's not both. And it's not neither. So an alternating group of permutations, we denote that as AN. That's the set of all even permutations in Sn. So nothing crazy here. AN is just grouping together into one set all of the even permutations in Sn. Theorem 729, it says Theorem 729 actually says AN is a subgroup of Sn of order n factorial divided by 2. But at the top of this card, I just kind of split it up into those 2 important things. AN is a subgroup of Sn. Like, we don't have to even go through and prove it's a subgroup. We know from this theorem that it is a subgroup. So that would save time. And also the order of AN is n factorial divided by 2. And that's it. Yay.